Well, today the main goal is to focus on exponential functions, trigonometric functions, and an introduction to the complex logarithm. But I thought it would be good to do a few more things with what we were talking about the other day. We saw the linear approximation or amplitwist idea. That was a big focus of class on Wednesday. But we assumed that the derivative of the analytic function we were talking about was non-zero. What happens? So what happens at places where the derivative is zero? Let's see here. The example I have, well, okay, let's first think of this in terms of a real value mapping. So here I have a function of variable x. I'm thinking of x as a real number. I'm going to make an ordinary plot of it. It is quadratic, so the plot is going to be a parabola. Did you know that you can think of real functions as mappings too? Not just complex functions. Except instead of mapping a plane to a plane, you're mapping a line to a line. You're mapping the x-axis to the y-axis, or more specifically, subsets of the x-axis, like this line segment here, to subsets of the y-axis. If I move this lambda 1 slider, that line segment there on the real axis gets mapped up onto the graph initially, and then move the lambda 2 slider, it gets mapped over to an interval on the y-axis. So there is this quadratic function as a mapping for this particular set. We are, by first doing the lambda 1 slider, then the lambda 2 slider, we are seeing the line segment get transformed to a new line segment. I've got two other sliders. I can change the center of the line segment, x0, and I can change its width with a, and continue to see the mapping. And the reason I'm bringing this up is that now watch what happens if I allow my line segment to include the critical point for the quadratic. Maybe you can imagine what's going to happen. Move it to the left. Watch what happens now when we do the mapping. You go up to the graph, and then over to the y-axis, and it's like it gets folded over itself when we include the critical point in the original interval, which shouldn't be surprising because over that interval the function is now 1 to 1. Does something similar happen in a complex case? So here's a complex case, and I went ahead and picked a 5th degree polynomial there. What are its real and imaginary parts? They're kind of messy. Wouldn't want to have to do this one by hand, I don't think. What happens now when we view this as a mapping? Well, this is the set that I'm going to find the image of. This is its image over here. I can move the set around and see the image change, and I'm purposely, you see on the right side, allowing the axes to move so that it stays centered on the image point. That's the image of the center of the square. I can also increase the magnification over here. I can increase the size of the square or decrease the size of the square. What are the red dots on the left? You got a guess? Guess what these 4 red dots are? It's related to what I did up here, actually. This line. What do you think those 4 red dots are? Look at the solve. Those are critical points where the derivative is 0 for this function. All right, those 4 red dots. Notice this function had real coefficients. These two things are complex conjugates. These two things are complex conjugates. Its derivative has real coefficients, and complex roots of polynomials with real coefficients have to occur in complex conjugate pairs. I mentioned that on Monday, I think. That is something you should know. What happens if this set contains one of the critical points? Ready? Watch it here. We're going to cross one of the critical points. Watch both sides at once. We're getting close. We're getting close. What do you see happening on the right? You see it folding over itself. It's no longer 1 to 1 on this set. It's 2 to 1 on part of it, at least. There's some sort of folding action going on at critical points. No matter which critical point I look at, there's folding going on. Similar to the real case, but in a higher dimension. Is that still true even if my square is pretty small? Yes, it's still true, but it's hard to see. Which is why I allowed myself to zoom in on the right by decreasing R here. We can zoom in, and we can see there's still folding going on. Okay? So that's the kind of thing that happens at critical points. I also made a new kind of graph to allow us to visualize the amplitwist concept based on the values of the modulus of the derivative at the point and the argument, not at a critical point here. F prime of z0 is not 0. What do we see here? We see the function was a fourth degree polynomial. Actually, let's go to z squared to keep it simple. So now we're looking at z squared. Here's your z-plane, here's your w-plane. There's your square that you're trying to find the image of. You also see a contour map in the background. What's the contour map of? That's the contour map of the real valued function, which is the modulus of z. Excuse me, the modulus of z squared. Because the function is z squared. The modulus of z squared is x squared plus y squared. That's the contour map we're seeing here. We're seeing the level curves in the background. We can see the values there. This point is close to where the square of the modulus of z squared is close to 7.1 right there. So in terms of the amplifying part of the amplitwist concept, this should map to something that's kind of a square. You see it's not exactly a square. And where the linear dimensions are about 7 times longer. Seem reasonable? The scales are different. This goes out to 4 here and 10 there. This should be about, these blue and red vectors should be about 7 times longer than the blue and red vectors over there. Actually, it looks like the local dilation factor I have up here to be 6, so we're not quite up to the 7 there. What's the local twist amount? In degrees, it's 90 degrees. If I look at the contour map of the argument function, argument of z squared, I get this graph. Hover over these level curves here. This one, the argument's about 1.45 radians. What would that be in degrees? Let's see. 1 radian's about 57 degrees, I think. Does that sound right? This should be close to 90 degrees. 1.45 radians. The next level curve up here is 1.74. The argument of z squared is a bit bigger than the argument of z squared down here. If I move the cursor on the left toward darker regions, you can see the twist amount is getting smaller, where the argument is decreasing in value. Right about here, for example, if I can get there. Okay, right about there, the cursor is on a line where the argument's about 0.58 radians, evidently about 29.5 degrees. And that's the local twist amount of vectors. So it's kind of nice to allow yourself to have that in the background, both the absolute value of the function and its argument, to help you understand the amplitwist concept as well. I want to do one more thing with polynomial functions. You should be able to expand any polynomial function about any location, any z value. For example, if f of z is z cubed plus 3z squared minus 4z plus 1, should be able to expand this polynomial about some location other than 0 like it is expanded here. What am I talking about? I'm talking about Taylor polynomials, really. Can I write this in terms of powers of, say, z minus 2? Right? In terms of powers of z minus 2 instead of z. Can that be done? Yes, it can. There's two methods. I will show you both methods. The first method is to do a change of variable, essentially. When the book does its change of variables, they use a Greek letter called zeta that looks about like this. I was practicing using zeta before class, and it was difficult to make it very fast. So I'm going to use a different Greek letter, my favorite Greek letter. If I draw it slowly, it looks like this. Does anybody know the name of that one? Xi, yeah. When you anglicize it, I guess you spell it Xi, but you say Xi. Xi is real fun to make real fast as well. Ready? Okay. I might not make it great, but I can make it fast. Oh, that wasn't very good. A little bit better. Okay, so I'm going to use Xi. Some people just call it squiggle. Okay, that's going to be my variable name because it's fun to make. Let Xi equal z minus 2. Actually, let's see. Is that what I want to do? Yeah. So that means z is Xi plus 2. I'm going to now substitute Xi plus 2 into this function in place of z, simplify it, and then at the end, go back in terms of z, replace all the x's with z minus 2's. And that will expand this function in terms of powers of z minus 2. Let's do it over here. Actually, let's do it here. So what is f of the expression Xi plus 2? If I make my Xi bad, like that one's kind of bad, I'm not going to bother fixing it. Unless it's really bad. I'll take a eraser on there. Replace the z's with Xi plus 2. Xi plus 2 cubed plus 3 Xi plus 2 squared minus 4 Xi plus 2 plus 1. It's also fun to say, right? Xi. Expand this. There we get Xi cubed. Thinking about the binomial theorem, Pascal's triangle, 1, 3, 3, 1. The next coefficient is going to be 3. I'll get 3 Xi squared times 2. I'll get 6 Xi squared. And then I'll get 3 Xi times 2 squared. 2 squared is 4 times 3 is 12. Then I get a 2 cubed is 8. Try to check in your own mind with me so I don't make a mistake. Got to expand that out. Xi squared times 3 is 3 Xi squared. Then I'm going to get from foiling, I'll get a 4 Xi from outside and inside times 3 is 12 Xi. 2 squared is 4 times 3 is 12. Minus 4 Xi minus 8 plus 1. Simplify. Xi cubed plus 9 Xi squared plus 20 Xi plus 13. Is that right? Double check my work there. Now replace Xi, bye bye Xi. Replace it with z minus 2. And if I haven't made any mistakes, this is now an expansion of the original polynomial in terms of powers of z minus 2, which does have its uses, which I'll get to in a second. Look good? Okay, I missed the 12, okay. Wait. The 8's canceled. 12 plus 1 looks like 13, okay. There's another way to get this, and that's to use Taylor's formula. As a series, if you expand the function about some number c, you can write Taylor's formula like this. And for an arbitrary function that's infinitely differentiable, this is an infinite series. However, for a cubic, like this function is, this series is going to truncate. All the derivatives after the third derivative are going to be 0. So I guess I don't have to bother writing plus dot 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 here. This function is a cubic. We're going to be able to stop once we get to that third power there. Use the derivative with c equal to 2. We're expanding about c equals 2. So let's check that works here. Go back to the original function here. Let's find its derivatives as well. F prime of z is 3z squared plus 6z minus 4. F double prime is 6z plus 6. And F triple prime is 6. Now plug into all these things. We're expanding about c equals 2 when we write it in terms of powers of z minus 2. F of 2, going back here, is 8 plus 12 minus 8 plus 1 is 13. That looks good. Matches the 13 there. F prime of 2. Plug 2 into there, I get 12 plus 12 minus 4 is 20. That 20 matches this 20, that's good. F double prime of 2 over 2 factorial. Plug in F double prime, plug in 2 into F double prime, I get 12 plus 6, 2 factorial is 2, I get 18 divided by 2, I get 9. That looks good too. Finally, F triple prime of 2 divided by 3 factorial is this constant 6 divided by 6 is 1. The coefficient of z minus 2 cubed is 1. All right? The book does an example just like this. You should be able to do this kind of thing both ways. What's the practical benefit of it? Well, certainly in terms of real functions, if z were a real number and we wanted to graph f of z near z equals 2 without technology, say, this form of f's equation would be more helpful than the original form when you want to graph it near 2. It would tell you that f of 2 is 13 for one thing. It would also tell you the slope at z equals 2 would be 20. So it would be pretty steep there. If we go through this point at 213, the slope would be 20. It would also tell you the graph is concave up because the second derivative is going to be positive. So if you wanted to give it a slight concavity, it would be concave up. After that, it gets more difficult. But if nothing else, it allows us to say the graph near this point looks about like that. Of course, it is a cubic, so you have other kinds of knowledge that you can use to figure out the rest of the graph as well. What about if z is complex? Well, presumably it's still useful. In terms of linear approximations, near the point 2, the linear approximation would come from that part. Thinking of that as a linear mapping, or linear mapping plus a constant, that could help you figure out what this looks like, how it maps small regions near 2. That would be an application of it in a complex case. All right, let's go on to our main topic of the day now. And that is going to be exponential functions, trig functions, and the logarithmic function. Complex logarithm, which we will see, just like the argument function, can have more than one value. An example of a multi-valued function, which sounds like that's not allowed, right? Haven't you always learned since when? Maybe 9th grade? I don't know, 8th grade? That functions always have one output. Otherwise, it's not a function. Well, technically that's true. Still, functions have to have one output for every input. But if we decide we want to allow these things that have more than one output, like the argument, we just change the terminology. We call it a multi-valued function. That's okay, right? Just change the terminology. Or if we're feeling lazy, we still call it a function. But in our minds, we remember it's a multi-valued function. The logarithm is going to be multi-valued. We'll see why here in a few minutes. The complex exponential, we already know the formula for that. Exponential. We already know e to the z is e to the x plus iy is e to the x times e to the iy. Using Euler's identity, expand this out, you get e to the x cos y for the real part, and e to the x sine y for the imaginary part. There's your complex exponential. What do we know about this so far? We know it's differentiable everywhere, therefore it's analytic everywhere. It's entire, and its derivative is itself. That's something we know already. I also did mention, maybe about 4 or 5 lectures ago, that it's actually periodic. But the period is not a real number. The period is a purely imaginary number, periodic with period 2 pi I. Give me any z, plug in z plus 2 pi I. Use the property of exponents, which we know also holds. And use the fact that e to the 2 pi I is 1. This is the same as e to the z for any z. It's periodic with period 2 pi I. What about its mapping properties? It's helpful to think in terms of polar coordinates here. The modulus of e to the z is the same as this. But this thing here is 1, right? That's always on the unit circle. E to the iy, where y is real. It's always on the unit circle. And e to the x is always positive, where x is real. So this is the same as e to the x. The modulus of the output is always e to the x, e to the real part of the input. What about the argument? Well, it's y. Yeah. Thinking of it this way, that's real. That's on the unit circle with angle y. In radians, if you like. So the argument of this is the same as the argument of e to the iy, which is y. What does this mean as far as mapping properties? Think about how this would map an infinite strip. Say, whose boundary on the bottom is a horizontal line at negative pi I, if this is the complex plane. The imaginary part is negative pi. And whose boundary on the upper part is not included in the set. And that upper boundary intersects the imaginary axis at the point I pi, or pi I. Consider what would be the image of this set under this mapping. That might be easiest to think about in terms of initially thinking about what is the image of any horizontal line here at a fixed value of y. So we are thinking about what are the values of this quantity at a fixed value of y as x varies. At a fixed value of y means you're at a fixed angle. And based on what I've drawn here, it looks like the angle might be about negative pi over 2. Let's pretend it's not that exactly, but close. The angle for the output's always going to be close to negative pi over 2. It's always going to be on this line, say, where that angle is y, which is a negative number here, is at the entire line. As x varies from minus infinity to plus infinity, this quantity e to the x varies from 0 to infinity, and it's never equal to 0. It's going to trace out the entire array as x varies from minus infinity to infinity, excluding the origin. Because the modulus does equal e to the x. It's going to vary from 0 to infinity, not equal to 0. E to the x is never 0. You're going to trace out the entire array. The image is going to be the entire array except for the origin. Now let y vary from negative pi to positive pi. The image is going to be found by sort of piecing together a bunch of these rays, which include all the points in the plane except for the origin. The image of any kind of horizontal strip, this is called a fundamental strip. I included negative pi I and not pi I. I could have done it the other way around. I could have included pi I but not negative pi I. The image of any such horizontal strip is the entire plane except for the origin. And on such a strip, the function is 1-to-1 as well. But overall, the function is not 1-to-1. You consider more of these strips, they all map into the same entire plane except for the origin. We saw by doing some algebra with Euler's identity that we could derive formulas for cosine and sine in terms of the complex exponential. You remember that? And we used that to do integrals, to derive trigonometric identities that helped us do integrals. Problem or two came up on the exam like that. That derivation, could it work when the input for sine and cosine is complex? Well, essentially we define it to work. And that leads us to define cosine and sine when the input is a complex number in the following equations. Cosine of z is e to the iz plus e to the negative iz over 2, just like it was when z was real. Z is complex now. And sine of z would be e to the iz minus e to the negative iz over 2I, just like it was when z was real. These are now essentially definitions. They're consistent with the case where z is real. Are they good definitions? Otherwise, we will see that they are. Just as another reminder, dividing by I is the same as multiplying by negative I. You can also write the formula for sine z as negative I times e to the iz minus e to the negative iz over 2. That would be another way to write the formula for sine z. Are these good definitions? Well, they probably are good definitions if a lot of the properties, if not all of them, for trig functions in the real case carry over to the complex case. What's going to happen is a lot of the algebraic properties do carry over, but not all the properties. In particular, the modulus of the output is not always between -1 and 1. Not always, I should say, between 0 and 1. That's not true in the complex case. That's not really an algebraic property as much as the other properties that we're used to for trig identities. Is the derivative of sine z equal to cosine z? Will that property carry over? Certainly these functions are entire, by the way, since e to the z is entire. And since these functions are made up of, well, compositions of e to the z with I times z, and you're also doing arithmetic, these functions are definitely differentiable. To differentiate sine z, I got to differentiate, say, it in this form. Well, it doesn't really matter which form I use, but I guess I will do it in that form. Let me bring the negative I over 2 out in front. I really need to differentiate e to the iz minus e to the negative iz, then use the chain rule, get I e to the iz plus, plus I e to the negative iz, right? Differentiate iz, you get I times e to the iz. Differentiate e to the negative iz, you get a negative I in front times e to the negative iz, that's the chain rule. The negative I times -1 gives you a plus I. I can factor that I out, and then I times negative I is positive 1. This becomes 1/2 e to the iz plus e to the negative iz. That is the same as cosine of z. Likewise, and you can check this on your own, the derivative of cosine of z, I'll let you check it in a similar way, is negative sine z. That's true. What about cos squared plus sine squared? Does that always equal 1 in the complex case? Let's see what happens. Cos squared z plus sine squared z. Bottom's going to square to 4. The top, if I FOIL it out, when I square out the top, I'm going to get e to the 2iz plus 2, right? E to the iz times e to the negative iz, assuming properties of exponents hold, which they do, is e to the 0, which is 1. 1 plus 1 is 2. And then you've got e to the negative iz times itself, that's e to the negative 2iz, all over 4. Square the sine function, say in this form. Negative I squared is -1. Put a minus there. 2 squared on the bottom is still going to be 4. What happens when you square this out? You get something similar to when I squared that out, except with a -2 instead of a +2. And hopefully you can look at that and say everything cancels except for the constants. And the constants give you 4 over 4, which is 1. So, yes, your fundamental Pythagorean identity still works. I like that, right? That's good. You want that to work. What about other trigonometric identities? Is it still true that, for example, sine of 2z is 2 cos z sine z? That would be a double angle formula. A question mark there. Is that still true? Let's see. Turns out to be easiest to work with the right-hand side first, actually. What does 2 cos z sine z equal? use this form of sine z. Well, maybe I shouldn't. Maybe I should do the I in the bottom there. Let's put it in the bottom. This 2 cancels with that 2. So you're left with a 2i in the bottom. FOIL out the top. First times first gives you e to the 2iz. Outside times outside gives you 1. Negative 1, excuse me. Inside times inside gives you positive 1. You get minus 1 plus 1. Those cancel. Last times last gives you minus e to the negative 2iz. The 1's cancel. And that is the same as sine of 2z. That one works. Yeah, all the other algebraic ones, purely algebraic, symbolic ones work. They are mentioned on page 113. But not all the ones that could be listed. Those are the most fundamental ones. They work in the case where z is complex. What does not work? Well, take for example, the modulus of cosine of z. Say in the case where z is purely imaginary, to keep it simple. Okay, keep it simple. I'm plugging in a purely imaginary number, y. What will happen here? Let's see. We get e to the negative y plus e to the y over 2. We get this expression. We get really the cosh function applied to y. And if you think about that, try to imagine graphing that as a real valued function here. What would its graph look like? You're really doing a linear combination of 1/2 e to the y, or e to the y and e to the negative y. We're talking ordinary graphs here now. 1/2 e to the y looks like that. 1/2 e to the negative y looks like this. When you add those two functions by adding their graphs, so to speak, add their outputs, you're going to get a graph that evidently is going to look something like this. And if you think about it, if you plug in y equals 0, it's going to be a minimum, and you're going to get 1. When you plug in y equals 0, the vertical intercept there is 1. This function, cosh of y, never goes below 1. So not only is this fact, or this claim, not true, it's badly false in the case where your input is purely imaginary. It never gets below 1. So that property of the modulus of the output that we might have hoped was true is not true in the complex case. Should sinh and cosh be defined in the same way as in the real case? Well, the answer is go ahead and give it a try and see if it seems like a good idea. And it is. Cosh z is e to the z plus e to the negative z over 2. Sinh z is e to the z minus e to the negative z over 2. There's no i's in there. where z is complex here. Are the properties of cosh and sinh consistent with their real properties? The answer is yes. You can check the derivative of cosh is still sinh. The derivative of sinh is still cosh. No negative signs. You can also check, I'll let you do it, that cosh squared z minus sinh squared z always equals 1. In the case where z was real, that was what verified that cosh and sinh, these hyperbolic functions, could parameterize hyperbolas. In the case where z is real. There's also some nice relationships between the hyperbolic functions and the trig functions. They are related to each other. Which then makes it less surprising that their derivatives act in similar ways, for example. For example, could I write sinh or sine of iz in terms of sinh or cosh? It turns out you can. Go to the formula for sine. Let's use this form of it. Replace z with iz. Z is complex here. I times I is negative 1. Negative I times I is positive 1. We still have a 2i in the bottom. I could bring the division by I out in front as a negative I. And then I could switch around the order of the things on the top there and get rid of that negative sign. And that's a good idea because that helps you see a nice relationship between sine of iz and sinh of z. It equals I times sinh of z. And there are similar properties relating cosine of iz with cosh. And in fact, sinh of iz and cosh of iz with sine and cosine. And they're in the book. I'll let you look at them. They're on the bottom of page 114. What does this mean geometrically, thinking in terms of plugging complex numbers in? It means that this dealing with sine and sinh in this way with this factor of I, it's almost like it's a kind of operation preserving. It doesn't matter which order you do it. You can either take your z, multiply it by I first, in other words, rotate it by 90 degrees, before plugging into the sine function. You're going to get the same answer as if you took your original z, plug it into the sinh function, and multiply by I, rotate that answer by 90 degrees. Turns out to give you the same thing. Let's check it with a particular example. And just see that kind of thing in action. If my initial point, for example, is, say, 1 plus 2i. What is sine of 1 plus 2i? It's about that. What happens when I multiply that by 90 degrees, pi over 2 radians? Oops, I didn't mean an I there, I meant a percent sign. Think geometrically with me here. This complex number I need to get new blues for the board here. This complex number would be right around, say, here. If I multiply it by, excuse me, I did want an I in there, sorry. Or, if I multiply it by I. If I multiply it by I, that's going to rotate it by 90 degrees, so I'm going to get a quantity some point right up there, whose real part is negative and whose imaginary part is positive. In fact, if you think about it, probably what's going to happen, well, I mean, if this happens algebraically, is the real part's going to be the opposite of this imaginary part. And the imaginary part's going to be this. That's what's going to happen when you multiply by anyway. If I multiply the original thing by I first, I get negative 2 plus I. So the original thing, 1 plus 2i, is, say, well, right about here, say. There's 1 plus 2i. Multiply that by I rotate it by 90 degrees, I get negative 2 plus I. Evidently, plugging that into the sinh function gives you the same final output. Yep. I don't know how enlightening that is, but it does re-emphasize the geometric interpretation. One final thing I want to do here, and I do want to end class early. I want to get the logarithm, but I also wanted to mention something else. Let's do the logarithm for 5 minutes, and then we can go early. Introduction to the complex logarithm. For a given point z, z non-zero, what are the solutions of the equation z equals e to the w? In other words, what values of w will make that true? To help you figure it out, and therefore, evidently, if you think about this, to find the complex logarithm. If there are solutions to this, we should probably call them logarithms, right? It's helpful to write z in polar coordinates and w in rectangular coordinates. Say z is r e to the I theta, and w is u plus iv. Then this equation, z equals e to the w, is then equivalent to r e to the I theta equals e to the u plus iv, which is e to the u times e to the iv. In order for these two things to equal each other, certainly r does need to equal e to the u, because that's the modulus of both of these numbers. The moduli have to be the same if these numbers are going to be the same. The arguments, though, theta does not have to equal v. Theta can be some form of the argument of this, but it's not necessarily equal to v. It equals v up to some integer multiple of 2 pi. R must equal e to the u, and theta must be v plus some integer multiple of 2 pi. 2 pi times k for some integer k. Well, this equation means u must be the natural log of r. And this equation is equivalent to v equaling theta plus 2 pi k. And I could write minus 2 pi k as well, but I'll go ahead and write plus 2 pi k, since k is any integer. So any number with the property, any number w with the property that its real part is the natural log, the ordinary natural log of the modulus of z, and whose imaginary part is the same as the argument of z plus some integer multiple of 2 pi will be a value of w that makes this true. Will be a solution to this, and therefore will be a logarithm of z. In complex analysis, it's traditional to no longer use ln. That's my final comment of the day. But it's spring break. Well, unless you got it right classes. Okay. It's traditional to call this LOG, and in fact, capital LOG now we're going to write both little log and capital log after spring break. Little log is the multi-valued complex logarithm. Capital log is the principal value of the complex logarithm. And yes, we no longer write ln. Well, that's a little bit of a lie. Some people still write ln. But lots of people don't, and our book does not. For the real natural log, they write capital log, which can be defined for complex numbers too. It's called the principal value, just like there was a principal value of an argument. It's going to be related to the principal value of the argument. Have a good spring break. So what